Good evening, ladies and gentlemen here in Brazil, and good morning there in Australia. It is my pleasure to present the 10th IFSP webinar of the Extension Project entitled as Educational Practices for the Sustainable Management of Water Resources, supported by the Tropical Water Research Alliance and the Australian Embassy in Brazil. The purpose of this webinar is to address the challenges for the sustainable management of watersheds regarding the mitigation, adaptation, and resilience to extreme events and climate change. My name is Vasiliki Bolomitis, and I am an Associate Professor of Water Engineering at the Federal Institute of Education, Science and Technology of São Paulo, and currently the coordinator of the Faculty of Civil Engineering and the Secretary General of TWRA in Brazil. Before presenting our speakers, I will give you a brief explanation about the dynamic of this online event. Well, after each speaker presents, all attendees will have the possibility of submitting written questions using the chat or the Q&A button, which is on the bottom of the screen. I will try to ask all questions here, but it will, of course, depend on our time schedule. You can choose to follow the presentations in English or in Portuguese. For that, you just have to select the language you prefer at the globe button that is on the bottom of the screen. Well, I feel very honored tonight to present our three speakers. Unfortunately, the fourth speaker will not be able to present because of a health issue. But tonight we have here Dr. David Hamilton, Dr. Stuart Pan, and Dr. Nick Bond. They are remarkable researchers in Australia and very well known worldwide, and will contribute a lot to enhance our knowledge on the field of water management, particularly facing problems due to extreme events and climate change. Our first guest is Dr. David Hamilton. He's the Deputy Director of the Australian Rivers Institute and a professor at Griffith University. He has held positions in environmental engineering at the University of Western Australia and biological sciences at the University of Waikato in New Zealand. His research has involved testing and modeling of lake restoration actions and more generally documenting the trajectory of recovery of freshwater ecosystems. In recent years, he has been closely involved in management and policy implementation for freshwater ecosystems, holding appointments with the Ministry for the Environmental Agencies in New Zealand and advisory roles for regional councils and industry groups, New Zealand and in Australia. Today, Dr. Hamilton will be sharing with us his experience about the water quality risks under low and variable water level conditions in dams and reservoirs. So let us welcome Dr. David Hamilton to our event. It's a great pleasure for us to have you here with us tonight, Dr. Hamilton.
Well, thank you very much for that introduction. That was very nice. And I wanted to say good evening to you or good morning to some of us on the other side of the world. And I look forward to talking to you and hopefully receiving some questions. I'm going to be talking about understanding water quality risks under low and variable water level conditions in dams and reservoirs. And this is a subject that I'll be talking mostly about the Australian situation, but it has a global significance. And I'm well aware that you in Brazil have undergone some major problems and issues with availability of water in recent years, particularly with prolonged drought. Now, I'm mostly talking about a project that has arisen, and it came about initially, I guess, in 2018, and it was revolved around a catchment management community of interest. And the project was understanding water quality risks under low and variable reservoir conditions, also linked to dead zones and the yield from reservoirs. And this work was subsequently funded with the assistance of Water Research Australia. Water Research Australia helps to coordinate research for water utilities across Australia. There has been quite a lot of prior work related to this project. And the prior work is focused mostly on impacts of climate change on reservoir water quality, but not specifically on water levels. And this prior work identified that we could expect to see increased duration and strength of thermal stratification with climate change, potential for a reduction in water quality, and the need to increase work to develop confidence in management actions, for example, that may be used to reduce nutrient runoff in catchments, and to examine ways to redress the increase in stratification that could be expected with climate change, particularly through techniques such as artificial destratification or mixing in lakes and reservoirs. Other work that has been coordinated through Water Research Australia has been to consider how extreme events might affect water that's sourced from catchments for drinking water quality. So some of the consequences of large flushes of nutrients from storm events may result in increased risks of cyanobacteria or blue-green algal blooms. In coastal catchments, extended droughts increase the risk of saline intrusion from groundwater, and that may affect some of the lowland and floodplain storages. There's been no single or simple answer for managing these problems, and a combination of investment in green infrastructure to enhance resilience of catchments to floods and droughts, and grey infrastructure to improve water treatment are probably going to be most likely required. Now, I wanted to put a perspective on what we are looking at. So as we go through a crisis of climate, whether that be through floods or heat waves, it's always useful to put a historical perspective on things. And for example, the Millennium Drought, which took place in Australia around 2002 to 2009, was a horrendous drought because it's also seen to be recent and plays on people's minds. But we can go back to the turn of the 19th century when there was a similar severe and prolonged drought. And that drought lasted roughly 11 years, when rainfall was almost absent in most of Western Australia. This figure, though, paints a different perspective of climate change. And one thing that is persistent and ongoing, of course, is the increase in temperature. Since the Federation drought at the turn of the 19th century, temperatures have risen by about 1.4 degrees Celsius in Australia. And notably, the hottest month of the year has, in recent years, been extremely hot. And you can see that in about 2017, the temperature for January was elevated about 3 degrees Celsius above normal. So this heat wave is persistent, and it's been setting records, particularly in areas of central Australia, where temperatures have now approached 50 degrees Celsius in some cases on hot days during summer. And we can also link the heat wave to some of the severe drought that's occurred in recent times. And probably as a result, Australia's experienced some of the most severe rainfall deficits ever recorded. And one recent example was during the period from April 2018 to February 2020, when through much of central Australia, the rainfall was amongst some of the lowest ever recorded. So for major cities in Australia, this has created something of a crisis. Cities have continued to grow, and even with our best water use efficiencies, the demand for water has continued to increase. At the same time, water inputs to dams are projected to decrease, affected directly by temperature, but even more by the effect of that temperature on evaporation. So that by 2070 or so, we may see a reduction in runoff by about 40% or so in some areas. And this is very much related to the increasing temperature affecting evapotranspiration. So this combination of increased demand and reduced supply is potentially going to be catastrophic in terms of projecting out with our current levels of water availability. And it's potentially going to be met by very costly options, such as desalination for major cities, and increased water efficiency where that is possible, and in some cases, recycling. So I did want to introduce a case study to you. It's one that I'm very familiar with. It's Wivenhoe Dam, a very large dam that is critical for the water supply of Brisbane in Queensland. And it supplies roughly 60 to 70% of Brisbane's water supply. So as you will note, the Millennium Drought was a major driver for the decline in water levels that occurred between about 2001 and 2009, to such an extent that the dam at its minimum level during the Millennium Drought was less than 10% of capacity. So plans were actually being made that Brisbane would run out of water. It had severe water restrictions, and it also started to activate a water recycling plan, and desalination was also implemented. Let's have a look more closely at the relative, what we see is the relative lack of variability of water levels in Wivenhoe Dam in any given year. So in this case, you will note that there's about 4 years or so, 3 to 4 years, when there's a separation between times when water levels are increased between the minimum and the maximum. So you can see here in 1992, here again, 1999, to some extent in 1996, 2011 when there was a major flood, and 2013. So those are the times that about every 3 to 4 years, there is a major flood that comes through and boosts water levels before they start declining again as a result of the demand that exists for water. The characteristic of the Millennium Drought was that there were none of the flooding flows that occurred until about 2008 or 9, when water levels started to recover. So typically in the subtropical region, we have these infrequent flood events about every 3 or 4 years, and they are also associated with very poor water quality, often with flooding that leads to major damage to urban infrastructure downstream. We've looked at whether El Nino or La Nina events affect the storage volume variations in, for example, Lake Wivenhoe. And this is not the case, that there's no obvious relationship between El Nino and La Nina in this part of the country. That's not to say there aren't some relationships that exist, particularly for other parts of Australia, but nothing obvious in this subtropical region of Australia. So as you know, Australia is a country of extremes, and these extreme events can be expected to increase in the future with climate change. At the beginning of this year, the southern parts of Australia were in severe drought, and we had massive and unprecedented bushfires, particularly that is in the southeastern part of Australia. And these bushfires not only had severe impacts on vegetation and wildlife, but also resulted in some very high contaminant loads going into some of our lakes and reservoirs. And that necessitated some remediation measures. So this photo shows a curtain installed near the inflow of the Upper Yarra Reservoir in Victoria, which is part of Melbourne's water supply. So bushfires have drastically affected the composition of water entering some of our reservoirs, and this outcome appears to actually be quite persistent and has necessitated remediation actions such as the case that you see in this photo. So what sort of changes can we expect in terms of water quality as a consequence of climate change? There is a major concern that we will see increased frequency and intensity of cyanobacteria blooms in association with increased temperature, but also, and in fact primarily, because of increased temperature stratification, which will favour the proliferation of buoyant cyanobacteria that can form surface blooms and scums. So there are other factors that may favour cyanobacteria also, including the intermittency of nutrient supply that's associated with droughts and floods. And so these intermittent conditions are actually quite favourable, together with increased temperature and more stratification, to favour the occurrence of cyanobacteria blooms. And we might also expect to see changes in the distributions of species with climate change, potentially leading to the sort of niches that may favour colonisation by invasive species that would not normally occur in some regions. So this slide summarises some of the water level effects that I have been talking about. Littoral resources play a key role in the trophic structure of lakes. Native species are mostly not well adapted to extreme water levels beyond the normal range, and invasive species may therefore be able to establish. And there may be a lot more nutrient cycling as waters become warmer, and there is greater surface area of bottom sediment relative to the volume of the lake. So in summary, what we are likely to see is a shift from the current state, denoted by the black line in the top left panel here, excuse me, to a future state where the incidence of droughts and floods is likely to increase, as represented by this dashed line. So each of these extremes is going to shift water quality, with expectations that under low water levels, we might see increased salinity, more cyanobacteria blooms, greater turbidity, internal nutrient loading increasing, and also dieback of macrophytes under low water levels. By contrast, under high water levels, we might see more risk of dams being compromised and downstream floods, sedimentation in the dam, increased turbidity, and potential problems with microbes or pathogens. So each of these two cases or extremes can be expected to increase with a changing climate. So that brings me to a close, and essentially this is a project that we have running with Water Research Australia, looking at water quality impacts from extended drought and low and variable reservoir levels. And I'm just listing some of the research team here that has been involved in that project. So thank you very much.
Thank you so much, Dr. David. for sharing all these important topics regarding all the risks we have to face for the effective management of lakes and reservoirs. We have some minutes for questions, and I'd like to start with this first question, if you may allow me. One of our attendees is asking if you could give us some examples of how the green infrastructure could improve the conditions of coastal watersheds regarding the saline intrusion.
That is a very good and specific question. I suppose that one way is that green infrastructure, in other words, natural coastlines, have the capacity to be able to mitigate the vegetated coastlines, have the ability to mitigate erosion and therefore to potentially stop the intrusion of, at least at surface level, of groundwater into of saline water, saline surface waters into coastal regions. So that saline water in coastal regions occurs obviously from freshwater extraction, and it also occurs from sea level rise and greater coastal inundation. So using natural vegetation to stop at least and mitigate erosion in coastal regions is particularly important. And being able to, I guess, regulate natural ground and bring about more natural groundwater levels through natural vegetation in coastal catchments will also be important to prevent some of the extremes of drawdown of freshwater aquifers in coastal regions.
Thank you so much, Dr. Dave. There is another question here regarding the watershed management in Australia, considering how effective the decision-making process is, considering that Australia has the same issues we have in Brazil. We say that Australia is the country of extremes, but sometimes we share the same extremes here. Mm-hmm. We do have lots of bushfires, floods, and our social conditions are extremely different, but the natural phenomena are quite similar. So the question is, do you believe the decision-making process of the watershed committees there in Australia is effective towards regulating these risks that we have to face because of, you know, the climate change and extreme events?
So most of the major cities in Australia have water supplies that have very good regulation in the catchments. And so it's extremely fortunate that most of the catchments are in fact natural. There's very little, or mostly very little, development in those catchments. Now in Queensland, we're a little bit different because the water utility there only owns less than 5% of the land within the major water catchments for Brisbane. So that is a major risk factor, and it means that on the one hand, you can have potential economic development in those catchments, but you trade that off with the risk of potentially more pathogens, more nutrients, and degraded water quality in those catchments. So what you're doing is essentially you're balancing the green infrastructure, if you like, which is the natural vegetation in those catchments, where if you have it, you need a very low, minimal level of water treatment. On the other hand, for many of our water supplies here in Queensland, they actually require quite extensive investment into the treatment aspect of it, the grey infrastructure aspect. And the famous example, of course, is New York's water supply, where the investment was made many years ago into the catchment and being able to protect many of their catchments and have a very low cost water supply for New York. Now, that works well mostly for the cities in Australia where catchments are protected, but there are many inland and rural communities that are dependent on water supplies, many of which are quite critically threatened now because of climate change, and are also under intense pressure for irrigation. And those are potentially our major problem areas at the moment. How are we able to sustain those water supplies and be able to manage that balance of water, of best use of water?
Great answer. Thank you so much. Well, there are lots of other questions. Can you still keep on answering them?
Yeah, I'll go and
Thank you so much.
answering them.
Everybody's excited about your speech and they want to ask more and more. That's very good. Well, there is one question here. It's very technical. And well, there is a difference between the data collection we have here in Brazil and also the data collection you have in Australia, and also the number of gauges you have there. And there is one question here related to that. The attendee is saying that if we have this collection for not so long, can you conclude that these effects are due to droughts or floods?
Yeah, I've just started actually a project which is looking at optimizing monitoring in response to mitigation actions in lakes and reservoirs. And so that monitoring is actually very key relative to the level of investment in the mitigation actions. So many of these mitigation actions are actually extremely expensive, but they're not being adequately supported with monitoring that complements whether or not you can see the change. And really what you want to be able to see is this gradient of a short-term mitigation that has intense monitoring to detect change and a longer-term monitoring that may be associated with climate change and climate change impacts, where you need long-term monitoring to be able to support the evaluation of the changes that you see. It's quite a challenge.
It is everywhere. Thank you so much. There is another one here. I don't know if it is actually regarding your area there in Queensland, but it said here that mineral processing needs a lot of water. How dangerous is it for the coastal biome regarding the desalination process?
Yeah. So that's been a major driver to the considerations of desalination. So as you're probably aware, there's a brine that is associated with the desalination process, and that brine needs major dilution, otherwise it's going to affect the coastal biota. And so a key part of the evaluation of the desalination that's occurred, and we have desalination plants on the Gold Coast in Queensland, in Sydney, Melbourne, Western, and in Perth. And so a key part of those considerations has been the ability to dilute that brine and not affect coastal biota. So quite extensive preliminary studies beforehand.
Great, thank you so much. Here, Ms. Jennifer Panison is saying thank you, congratulating you for your speech. And she's also asking you if, what bioindicators and biomarkers are used to assess these impacts related to climate change in the reservoirs?
So you can look at a gradient there from physical to biological and other sensitive, potentially sensitive indicators. Obviously, a key indicator is temperature, but there's also stratification that follows. And there's also the levels of dissolved oxygen in the bottom waters. So as the stratification period extends, there's a greater likelihood that you'll get depletion of oxygen in the bottom waters of stratified systems. And in terms of other indicators, we actually use, in many cases, a range of indicators from trophic level index, which many countries sort of use based on nutrients and chlorophyll. An indicator of lake macrophyte health, which is actually known as Lake Spy, which is a New Zealand one that's used. And in some cases, other indicators such as zooplankton. So it sort of grades from physical indicators, where you're looking at the effects of temperature, to some of the outcomes in terms of oxygen and trophic status, and then perhaps some of the sensitive species that will be affected.
Great, Dr. David. Thank you so much for joining us tonight.
My pleasure.
It's impressive to see how the audience got connected and asked you so many questions. Thank you so much. We really appreciate it. Well, we will now proceed and present our next guest speaker. This is Professor Dr. Stuart Bunn. Professor Bunn is the director of the Australian Rivers Institute, also at Griffith University. His major research interests are in freshwater ecology, with a particular focus on the science to underpin river management. Dr. Stuart Bunn has extensive experience working with international and Australian government agencies and industry on water resource management issues. He is a member of the Murray-Darling Basin Authority and has previously served as a National Water Commissioner and as a Director of Land and Water Australia. In 2019, Dr. Stuart was appointed as a member of the Earth Commission hosted by Future Earth. Tonight, he will show us the best ways to build the catchment resilience. It is our great pleasure to introduce you, Dr. Stuart. Thank you so much for coming. We wish you have a nice speech.
Thank you very much, Vasiliki, and thank you everyone for joining us this evening in Brazil. It's great to be able to speak to you again. Building on what David has just spoken about, I wanted today just to outline a large project that David, myself and a group within our institute have been doing, which really aims to address this issue about how do we make our catchments, our watersheds, more resilient, particularly to extreme weather events. Can you see my slide okay there, Vasilika? This should be the main presentation.
Yeah, it is right? Perfect. Yeah.
Okay. So I suspect, as we see not only in Australia but also in Brazil, that tackling diffuse pollution is a really major problem, and to a large extent this is down to dealing with legacy issues that have resulted from past decisions around land clearing and land conversion. And certainly in southeast Queensland, which is the region that we're sitting in here, this is a region of about 24,000 square kilometres. The city of Brisbane is right in the middle. Diffuse pollution is one of the major threats that we're trying to tackle in terms of improving water quality. And the cause of this is pretty simple, that it just during major weather events, particularly storm events, which are increasing in frequency and intensity, these lead to major erosion within our catchments. That erosion makes its way into our reservoirs, our drinking water reservoirs, and ultimately out into the major coastal regions. And part of the problem there is it threatens an area of considerable significance from a biodiversity perspective. This is the Moreton Bay region here. The receiving water body, if you like, is a Ramsar listed wetland and has very large populations of dugongs and turtles. It also supports a range of commercial and recreational fishing. We really understand what the cause of that problem is. And as I mentioned, it really comes down to the poor condition that our catchments are in at the moment, and particularly the condition of the riparian lands around our waterways. So in the region of the 40-odd thousand kilometres of stream channel, about half of them have their riparian vegetation either degraded or in very poor condition. So that clearing of catchment vegetation, particularly clearing of riparian vegetation, is a key factor. And that's compounded now by alterations to the catchment hydrology. Because of the clearing of vegetation, we see that in any given major rainfall event, the water runs off the landscape much more quickly. It gets concentrated in gullies and channels, and that really, because of the lack of riparian vegetation, results in a significant erosion. Now, we think of this as a major environmental problem, which of course it is, but it's becoming increasingly apparent that there are significant economic and social costs associated with this, that there's the flood damage that we get to bridges and roads through extreme weather events. We see with every major flood event significant loss of valuable farmland as riverbanks and floodplains erode. We see increased costs of water treatment at our major water treatment plant for the city of Brisbane. And in fact, in the most recent flood in 2013, the city almost ran out of drinking water because the treatment plant was overwhelmed with sediment and debris from the catchment. And there's a whole range of other economic costs as well. The cost of dredging the Port of Brisbane, the loss of water storage within our reservoirs. And we've been working quite a lot to capture what that economic cost is in addition to the environmental problems that we see. Now, these sort of challenges will be, I think, very familiar to many people in Brazil as well. That what we're seeing is that most of the impact and most of the costs associated with this are usually borne by those who are living downstream. And most of the solutions, the things we need to fix, are, of course, they're upstream where the money typically isn't. What this means, though, too, is that it really requires targeted investment. This is very much a spatial problem because we know from work we've done that here and around the world that most of the pollution is coming from a very small part of the channel network. Here's an example from one of the small catchments in southeast Queensland. The red areas here represent about 10% of the total catchment area, but they're generating 60% of the sediment delivery to the river system. The yellow areas are another 10% of the catchment area and generate another 20%. So you can see that if we targeted our investment to these places in the landscape, we would be shutting down a major source of the problem. I'm not sure whether you can see it on your screen, but the little yellow dots that are distributed around here and the little red lines represent where actions have been made in the past to address this problem. And this really, to my mind, highlights the nature of the challenge that we're facing with, that much of the current investment to tackle these problems isn't effective because it's poorly targeted and it's not at the right scale. The second part of the problem is that we really have, in the past at least, have failed to capture and quantify what the benefits really are. Not just benefits from sediment, but the other associated benefits with that. So the real challenge that we've been working on then is how do you choose what actions to take where? How do you optimise that investment to get the best outcome for the least cost? How do you work with stakeholders, people living in the watershed, industry partners, governments? How do you reach consensus about what is the right thing to do? And in particular, how do you build confidence amongst both from a government point of view, but also confidence in the landowners where you're proposing to make changes in the way that they're managing their land? So the project that we've been working on is really developing a multi-objective investment tool that really seeks to optimize, be able to enable you to explore different optimal solutions and use that in a very deliberative way to reach consensus. And this tool really tries to quantify what series of actions that we might be able to take, and for every action, what's the cost of doing that, both in terms of the cost of the actual action and the opportunity cost, the cost of lost production, for example, if we change land use, but also then quantify what are the benefits. And we've tried to capture the benefits not only in terms of improving water quality, the reduction of sediment and nitrogen in particular, but we're also interested in to what extent can we have an impact on the risk from flooding. And when we look at the overall scenarios, what are the benefits in terms of improved river stream health and carbon sequestration as well. So that's what the modelling tool that we've been developing has. And quite uniquely, I think what we've done with that is working to couple that with a visualisation interface. So we're working with another group who specialise in developing visualisation techniques. And our thinking there is that these visualisation tools, together with the investment tool, will provide a platform that we can use to engage with communities, explore different scenarios and allow them to be part of the decision process. So this is called the Building Catchment Resilient Project. As you can see by the logos here, we have a range of different partners that include our university partners, some consulting firms. We have state and local government who are interested in reducing the soil loss from farms, mitigating flood risk is a big issue. We have an urban water utility which is responsible for wastewater treatment. They're very interested in how can they maximise investment to offset the amount of nitrogen they're discharging. We have the Port of Brisbane, a Port Authority, because they're interested in reducing the cost of dredging. And we have the bulk water supplier for the city of Brisbane, and they're interested, of course, in reducing the cost of potable water retreatment. And a large part of the money that we've got has come from a philanthropic organisation, the Ian Potter Foundation in Australia, and together with some of the other non-government organisations like Healthy Land and Water, they're very interested in reducing threats to coastal ecosystems. Now, I don't want to go into this in any great detail. Just to give you an example, we're trialling a particular approach in a small sub-catchment called the Laidley catchment. And our project team largely centres around the group developing the multi-objective simulated annealing, the modelling platform that we're using. And that modelling platform really is taking into account what are the biophysical responses to different actions that we take in terms of nitrogen reduction, sediment reduction. And then we have a team that's working on those parameters. And then we have an economics team which is really focused on estimating what the costs and benefits of those actions are. So that's really in developing the modelling tool. And then that modelling group is really interfacing with a group led out of the Queensland University of Technology, which has been developing these visualisation tools. And hopefully I've got time at the end just to give you a little snapshot of what those things look like. Once we've developed and run the different scenarios, we can then take those scenarios and explore what the implications would be for flood risk, and also look at what some of the additional benefits would be in terms of carbon sequestration, for example, and river health outcomes. So what does the multi-objective tool really aim to do? It aims to choose what actions where, or show you what the options are to take different actions where. And it's really through this process looking to optimise your investment to get the best outcomes for the least cost. And we can represent that modelling output, if you like, in 3 dimensions, trying to optimise what are solutions that give you the best outcome for sediment, the best outcome for nitrogen reduction at the least cost. And each one of these dots on here on what is the Pareto front of those relationships represents a plausible scenario that we could look at. And so we have some scenarios. These are the different planning units, which might be really good at tackling sediment, but not very good at tackling nitrogen. We might have other scenarios which give you some sort of middle ground of a reasonable outcome for both. And there may be scenarios that give you a very poor outcome for sediment, a very good outcome for nitrogen, but are also quite costly. And so it allows, this modelling approach doesn't come up with a single solution. It allows people to explore what the trade-offs are between these different potential scenarios. The other part of the work that we've been doing, particularly in relation to trying to quantify what the benefits will be in terms of flood risk reduction, is we're using radar distributed rainfall information. So if we have a look at this particular plot here, this is our catchment. This was a rain event that drove the flooding in 2010. And when we hit the flood peak about here, you should see a black, very intense rain cell moving up the catchment as it comes down like that. And you can see that the rainfall is not distributed evenly. This tends to be part of the problem that we're dealing with. These rain events are highly episodic, they're highly spatially constrained, and we need to understand what the implication of that is on terms of the hydrology within the catchment, particularly the hydraulics within the catchment, to understand how our actions are going to be successful. We can take the rain on grid modelling, that rainfall distributed modelling, create a hydraulic model for hydrologic model for the catchment. This gives you an example of the calculated, estimated model, I should say, flood risk within that catchment. And if we zoom in on this area here, which is a very productive horticultural farm within the catchment, this middle plot here, which is that rectangle there, this is actually their farmland. The yellow areas that you can see there are places where the overland flow velocity was around 1.5 to 2 meters a second during that flood event. You see much faster velocities in the river channel at the same time too. But it's not surprising, given that sort of runoff, that we see the massive damage that was done to their fields and to their crops associated with that flood event. One of the other advantages of this method is that we can then explore what the implications of doing different land use change. And just as a very simple illustration, if we took the catchment upstream of that farm and just said, let's plant or replant riparian vegetation in a buffer strip all the way along the channel upstream, we can rerun the model and say, well, if you did just that one action, you would reduce the flood height by about 25 centimetres. You would delay the flood peak in the town at the bottom end of the valley by about 1 hour. And that's a really significant change in just one small management action. What a big impact it has on the hydrology in that system. We can also use the model to explore what the implications would be to the costs associated with flooding in the town. And the areas that we see here in the township at the bottom of the valley, the green areas that are illustrated here represent the houses that were flooded during that event that wouldn't be flooded if we would have done that sort of restoration. And so we can compare different scenarios and look at the different flood risk, and we can quantify what the economic damage you would have avoided had you done that. And that's part of the real strength of this modelling approach of bringing both the actions and the costs and the benefits together. So just to finish, I wanted to show you what we plan to do with that kind of output then is to marry the catchment modelling with a visualisation tool. And hopefully this should be streaming to you now. It's a little video clip that we use just as an introduction to this program. This gives you a sense of what the visualisation software is capable of. These are basically a platform that's used in gaming, making video games. And so we can use the visualisation to explore and fly through the catchment and zoom in on different parts of the landscape. And we can explore different scenarios and what actions we take where, and we're planning a series of interfaces that might show people what the costs and the benefits are of taking particular different kinds of management action within that. The tool that's being developed, the sort of state-of-the-art part of it. Ultimately, we're able also to use this in virtual reality as well, so enabling individuals to put on a headset and actually fly through the catchment, explore different kinds of management actions. You can really drill down and look in detail through this at the problems within each of the planning units, why they've been selected, and what the catchment would look like if you were to undertake that kind of catchment restoration. So look, I won't play the whole thing out now, but I'd be very happy, Vasiliki, to answer any questions if there are any. Thank you.
Thank you so much, Dr. Stewart, for sharing the goals, the strategies of your project. Amazing project, actually. And we would like to be part of that project because it actually involves everything, high technology, multidisciplinary collaborators. It's very nice. I actually have some questions here. We have a similar problem here in Brazil that some of our riparian forests, actually, we can say that most of them have been destroyed throughout this recent years, also before in the past, but recently, still with knowledge, people keep on destroying these areas. They do not believe that the effect is the one you said that you could model and predict. So my question is, have you already had any results by the engagement of the community? For example, by showing them that this may bring a different result. Have you already seen different results at that community, that people saw your prediction and believed on that and started leaving riparian forests or revegetating these areas, the areas that had been destroyed before? Have you already seen these kinds of situations in Australia?
Yes, we've done. I mean, part of the reason for showing you the Mulgowie farm, the farm area that we've been focusing on, two of our big industry partners here have already undertaken some demonstration style projects. They were actually quite large scale, but they've been done in a way that that they've been able to quantify what the benefits are in terms of calculated how much nitrogen per year they'll save and how much sediment they'll save. And the government has given the urban utility an offset for their nitrogen license and said, well, we calculate that this is saving X thousand kilograms of nitrogen per year, and so we'll credit you with an offset for that project. And really that's what we think can be used to drive the economics of it, if you like, to drive investment in this way, that you've got polluters like wastewater treatment plants, aquaculture facilities. They're all trying to operate within their license. This sort of approach would allow them to pay for it. In terms of whether or not, I think we have a very similar problem to the one you described, that two problems. One, I guess, is that a lot of the issues we're dealing with are legacy issues. They, you know, when Europeans first came here, they cleared nearly all of the vegetation. So a lot of it is not, it's not caused by current management, although there is still quite a lot of poor management of riparian land. But we also, part of the reason for doing the visualization and this modeling is that a lot of farmers just don't understand and don't really appreciate what the benefit that riparian vegetation can play. And so, and it's really hard to see that if you just go out and look at 5 trees.
Numbers, right?
And a lot of farmers where we are, I would say half of the farmers think that the trees cause the problem. And so, you know, these sorts of tools or these sorts of models, I think, are really quite important to show how, you know, if you change the whole catchment this way, how it might benefit you.
Mm-hmm, that's true. Once they see that, they start believing, right? Because sometimes it's hard for them just to understand what numbers show. If they get to see it, it's easier for them to understand, and also to see how the benefit will be to their own properties, right? Many of them have a huge loss because of floods. So we have some other questions here. There's one congratulating you for your speech and also saying, how do you think, based on the Australian experience, a community-based program could deal with diffuse pollution and work in the country, I think they meant countryside, as large and socioeconomic issues are uneven, the way it is, for example, in Brazil?
Yes, and well, and I guess that is particularly part of the problem, is that the cause of the problem in the upper catchments is usually the places where people can't afford to pay to fix it. The people who have got the money to pay for it typically are, you know, the city dwellers and the wastewater treatment plants downstream. So the only way that this can really happen is to have a scheme which directs the resources, starts to pay farmers or compensate farmers for the services that they provide by changing that. So if we were to try and implement this, we would be able to calculate on any particular farm, for example, that if you change your land use and set back and replanted trees, we calculate that would give you a credit of X kilograms of nitrogen, X tons of sediment per year. And then all we need then is to find a polluter downstream who wants to buy those credits and basically pay the landowner to change the way that they're doing. So we have to have some sort of incentive scheme that diverts money back. And in this part of it, in the catchment we're looking at, there are places there where farmers will make more money by doing this kind of intervention than grazing cattle or, you know, doing a little bit of planting that they're doing. So I think that's the way to do it, is to try and create an incentive scheme. And then the second part of that question, again, it comes back to this building confidence. You've got to be able to convince landowners that what you're proposing is going to work, and it's not going to be a problem. And so again, using the tools. The key thing about these tools is they're not meant to come up with an answer. They're meant to be used in a way that the community can come and explore different options and discuss all the different things that you do, rather than tell them what to do.
Yeah, it's actually a very effective tool to show them what decision might be made, because they might have several possibilities, right?
That's right.
So they could actually check the best options they have for the moment, and also considering short and long-term periods.
Yes.
That's great. There is another question here. He's asking if there is any kind of work using physical infrastructure, for example, micro dams, to retain the sediments coming from these devastated areas.
Yeah, it's a really good point. So there's a number of actions we can take. You know, there's a range of things we could do in the catchment. You know, we could change the grazing practice. We could replant and fence off the riparian zone. We could build small dams. Each one of those actions, we can, you know, there's a cost to do it. There's the cost to build it, and then there's the cost of maintaining and the opportunity cost if you're taking land out of production, for example. So every one of those actions is a possible thing you could do. The way that the modelling would work then is to explore what's the optimum selection of those things. So it may well be that some combination of planting trees in riparian zones, doing some on-farm restoration, putting in restoring floodplain wetlands might be another thing that we might do. And for each one of those actions, there's a set of benefits and there's a cost. And so what the tool allows you to do is try and optimize what suite of actions you would take. And they could be, as you say, they could be green infrastructure solutions, they could be engineering solutions as well. Our suspicion is that a lot of the green infrastructure ones will be cheaper and therefore be more likely to be selected in the optimisation. But there may well be some problems in the catchment that you really do need to have some hard infrastructure in to solve it.
Another question here. They're asking about, everybody's curious about how the law works in different countries, and they're asking about the laws in Australia, if they have protection laws there, considering the riparian forests.
Yeah, it's a really good point. Under the original English laws, there were for major watercourses in many states in Australia, because management of riparian land or management of waterways is a state government responsibility, not a federal. It's the same in Brazil. Well, it might be not in Brazil, but it's a state responsibility, not a federal responsibility. And in the old days, there was protection for what they called Crown land. The landowner didn't own the land adjacent to the watercourse. And that in many places, that's been eroded away over the decades. There are meant to be regulations restricting what people can and can't do in watercourses. But, you know, that doesn't stop bad things being done. And part of the problem, which I think which continues to make the problem worse, is that when we do have a flood, what tends to happen is a landowner will come out and say, well, what can I do to stop my property flooding again? And the only thing an individual property person can do is build their levee up a bit higher or straighten the river channel a bit more. And what they do then to solve the problem on their property is pass the problem on to the person downstream. And every time we have a flood event or a major storm event, we see people going out and doing that. And of course you just keep making the problem worse. You increase the stream power, you cause more erosion. The problem keeps getting worse and worse, keeps getting passed further and further downstream. So it really does require this whole of catchment scenario development, planning development to solve it.
Yeah, I think it's pretty much the same here. Sometimes we think we're talking about the same country. I think it's like that everywhere. Everything, I think that the purpose of our events, as you know, because you were one of the people that talked to us in the beginning of the process, is that we wanted to improve the knowledge of our community to be able to make better decisions at the water management process. So I think that education is the best non-structural measure that we have, because if people believe and see what the benefits are, they might start improving their local reality, and it causes a global effect, as you mentioned, right? Because it affects the downstream area. Once you do it in your plantation field, it will reflect on the other percentage on the downstream. Yeah. Thank you so much. Thank you so much, Dr. Stewart. Very nice presentation. I think that our guests might be continuing asking questions for you, Dr. Hamilton, but then please, if you could check the Q&A in case they have other questions. We will be doing it at the written way, because we have to keep going to Dr. Nick now, our next speaker. Thank you so much.
Thanks very much.
We really appreciated your speech, and thank you for sharing your knowledge with us. It was a pleasure.
Thank you. Thank you, everyone.
So now I'm going to introduce you our third guest speaker. It's Dr. Nick Bond. Dr. Nick is the director of the Center for Freshwater Ecosystems at the School of Life Sciences of La Trobe University, State of Victoria in Australia. His primary interests are in the effects of flow variability on riverine ecosystems, especially the landscape scale effects of floods and droughts. His research combines empirical field studies with innovative quantitative modeling approaches. He has extensive experience working on river management and environmental flow issues in Australia and internationally. His research focus is supported by active engagement with regional, national, and international water and natural resource management agencies to support evidence-based planning and decision-making processes. In his speech, he will talk about the climate change and water stress in Australia's Murray-Darling Basin. Thank you so much for coming here to join us, Dr. Nick. We would like now to welcome Dr. Nick Bond to our event.
Thank you very much. Just checking you can hear me and can you see the slides?
We cannot see the slides now, but
okay,
I can hear you properly.
I'll just try and share my screen again. Is that sharing now?
That's it. Mm-hmm.
You can see them now?
Yeah.
Great. Well, welcome everyone. Thank you for the opportunity, and thanks to both of the previous speakers, David and Stuart. Wonderful talks, and an honour to be sharing this opportunity with you. So I want to talk a little bit about water stress and climate change issues and how that's affecting water security in the Murray-Darling Basin in Australia. That's the focus, I guess, geographically, but some of what I'll talk about, and particularly the initial introductory slides, are taking a bit more of a global perspective and also looking at Australia as a whole. This first map I just want to show you to highlight the fact that water scarcity or water security is an issue that's facing a huge proportion of the global population and very large geographic areas, particularly in countries like Australia, in northern and southern Africa, in parts of South America, particularly in the south, including Brazil, and then also in areas like Central North America and parts of Asia. And this highlights that there are now many months, up to 12 months of the year in many of these areas, where there is simply not enough water available to meet all of the demands of both the human population and the environment simultaneously. And so that leads to the major focus for the work that I do and a lot of other people do, which is looking at how do we try and both firstly understand the consequences of that limited water availability. And my interest is particularly on how that affects ecosystems. But then how do we then also use that information in management discussions and policy making to actually determine where the appropriate trade-off is. And as David and Stuart have talked about, of course, there are a range of options and strategies that are also being implemented to try and reduce the degree to which those different competing uses are actually in fact in competition by increasing water use efficiency or finding novel water supply strategies. This map here just highlights the different patterns of how water is used in different parts of the globe, and you can see these bar charts here show the proportion or the percentage of water use that's used for domestic or agricultural or by industry. And in Australia, particularly in the Murray-Darling Basin, I'm going to be talking about, it's irrigated agriculture that uses the majority of the water. Somewhere close to 70%, or around 2/3 of all the water use in Australia is for irrigated agriculture. And that's a pattern that's repeated in a number of other regions. So in Asia, in Japan, in Africa, and in South America as well, we see agriculture the dominant pattern or use of water. But in Europe and parts of the US, for example, industry uses a much higher fraction of water. And those use patterns, the nature of the use has a strong influence on how the timing of that water, when it's used in the year, how it is actually captured and stored and so on. So securing water supplies in in these water-stressed areas is one of the first challenges. And this time series on this map that I'm showing you here, just we put together recently just to highlight the trajectory of dam construction in Australia. And so you can see on the map that the dots appearing as new dams are constructed. We're up to 1900 now, and we'll move through to 2020. And the graph on the bottom of the page is showing the cumulative total storage capacity of those dams over time. And in fact, what you'll see in a moment is there was a really intensive period of dam construction in Australia in the 1950s and 1960s. And that was the period in which irrigated agriculture really became a huge part of our agricultural practices. So we have over 800 large dams, and most of them, as I said, were constructed in the 1950s and 60s. And there's now a lot of discussion in Australia, particularly with climate change, as to whether we should be building more dams or not. And in particular, that's a discussion that's occurring for parts of northern Australia, where you can see there's actually relatively few dams, and yet that's arguably the area where there's the greatest amount of water available in Australia because of the tropics and the higher rainfalls in those areas. But we're also seeing now, with recent drought and climate change and renewed discussions about whether dams should be being either increased in size or new dams constructed in the Murray-Darling Basin. And it's an issue where many scientists would argue that it's not the right solution, but nonetheless, it's a popular viewpoint that's held within the community and by some politicians. So the consequences of those dams, many of you would be familiar with this, that they have a major impact on the natural variability and timing of river flows. This is Hume Dam, close to where I live, about 10 kilometres from where I live, and it's on the Murray River. It's a major storage that has greatly altered the monthly patterns of runoff in the Murray River. So the blue box plots here show the much higher average winter flows through the period of sort of June through to November. That we historically had much higher winter flows than we do now, and the median winter flows are now much lower in the river as a result of that regulation. But in fact, in summer, even though the river flows are never as high as they were in winter, on average they're now higher in summer, and that's because that's the time of year when water is released to meet irrigation demands. This graph here shows for different rivers within the Murray-Darling Basin the changes that have occurred in the average, or not average, but actually the maximum number of years between large flood events that inundate wetland habitats. This was some modelling work that was done about 10 years ago by our CSIRO, and the height of the bars shows the maximum interval between floods over the last roughly 100 years, going back to the early 1900s. And what you can see is that for some catchments, and is, for example, the Goulburn River here, Goulburn Broken River, the period that would have occurred prior to river regulation, we might have seen a maximum of 10 years between major flood events. That's increased threefold up to a more than 30-year interval between those inundation events that reconnect the river and the floodplain. And that has major consequences ecologically. This just shows from a plan view the reduction in the average number of days that different parts of the floodplain would actually be underwater due to annual flooding. And so this is again a floodplain area on the Murray River. And you can see that under the natural flow regime, there were parts of the floodplain where each year there would be many months, in fact, where the floodplain would actually be connected to the river. And those were sites of really high levels of biological production, important sites for fish breeding, for water bird breeding, highly productive habitats. And those now have been lost from many wetland systems. And so you can see the difference here in the duration on average each year of those inundation events, really large reductions for quite large parts of floodplains. So that paints a picture of the fact that we've already had a major impact on the flow regime on rivers in the Murray-Darling Basin and elsewhere. And we know that those impacts have had major ecological consequences. When we turn to look at the future, it becomes a major challenge as to how we're going to grapple with the impacts of climate change. And I'll just run through some of those impacts now. We've already seen, and this is work that's been done by the Australian Bureau of Meteorology, we've already seen over the last roughly 30 years that there's 20 to 30 years that's been changes in rainfall patterns. So we've seen major reductions in rainfall during what would have been our autumn and early winter periods from April to October. And that's particularly in the southern part of Australia, in the southwest and the southeast. And that was typically a time of year when farmers relied on rainfall to help plant their crops. But it's also the time of year when catchments are primed prior to winter, and the soils are wetted up so that when we get our winter rain, that we see higher river flows. The graph on the right here shows the rainfall during the northern wet season, which is the period from roughly October through to March. And you can see that in northern Australia and parts of northwestern Australia, rainfall at that time of year has actually increased. And that's due to that intensification of the climate under climate change, which is in many respects increasing the severity of water stress in what were already relatively dry areas and increasing rainfall intensity in those wetter parts of the planet. This is the same time series that David showed earlier, showing the mean annual temperature anomaly from the period of 1910 through to 2020. And you can see that there's been this significant trend in the annual mean temperature. This is specifically for the Murray-Darling Basin. I think David's might have been for the national data set. But there's this very clear signal in annual temperatures for Australia now. And again, as David pointed out, we're seeing that not just in the average temperatures, but also in extreme heat waves. And this graph here shows the number of days of extreme temperature that occur in Australia each year. And you can see that since the 1980s, there's been this very sharp increase in extreme heat days. And it's not just ecologically, we understand that it's not just the shifts in annual temperature, annual averages, but also these extreme events that is having significant biological impacts. And so one of the things that we saw occur in the Murray-Darling Basin in 2018 and 19 was a series of major fish kills that occurred in the lower Darling River. These occurred over several months, and there are a number of native species that were affected, including Murray cod and silver perch, golden perch and bony herring. Some of these fish, such as the Murray cod, are very large. They live for a long period of time. Some of these fish were estimated to be between 20 and 30 years of age. And this attracted global headlines in the news. And so many of you would have seen pictures of these events of many thousands of fish floating in these waterways as a result of these extreme events. And I was involved in an assessment to actually understand the cause of these events. And in fact, they were tied to the sort of water quality problems that we know can arise as a result of high temperatures, which was a combination of algal blooms and periods of warm weather leading to stratification of the water body, and then subsequently sudden changes in the weather with cold weather event, a cold front coming through, leading to a destabilisation of that stratified water body and mixing, which mixed the what was anoxic bottom waters in the bottom of these pools within the river, mixing that anoxic water right through the water column, which meant that there was no place where fish could continue to get access to enough oxygen. And so this plot demonstrates this. This shows here the temperature in the blue line over time, and the green line here is showing from day to day the actual relative change in temperature. And you can see these dots here show the 3 events where the major fish kills occurred, and they all coincided with very sudden drops in temperature, which caused that destabilisation and turnover of the stratified water bodies. Now, that was at a local scale, we understand quite well that was the factors that contributed to the actual mortality events of these fish. But one of the broader questions was, to what degree was that caused just by drought and changes in river flow? Was it over extraction of water, or is it perhaps even early indications of climate change? And that's actually in these rivers in the western part of the Murray-Darling Basin, where the river flows and the climate are naturally highly variable. Actually answering that question and teasing out those different causes is actually a very complex task, because the hydrology is just naturally so variable. But this plot here just shows for a number of the streamflow gauges in the Darling River, from the northern part of the Murray-Darling Basin down to Menindee, where those fish kills occurred. And I've highlighted here those periods of zero flow, so periods when these rivers stop flowing. There's a couple of gaps in the data which are shown in the grey areas, but if you look at this, goes back to 1980 through to 2020, and what we can see is that there is a clear trend at all of these gauges for much more frequent periods without any flow. And our conclusions was that it's almost certainly some combination of climate change and drought and extraction of water, that it's all contributing to some degree to these changes in runoff in the Darling River. So that gives us some insight into the challenges that we face when we look ahead at some of the climate change projections. And this map here just shows some work again from CSIRO in terms of their predicted changes under a wet, a medium and dry climate change model scenarios, changes in rainfall across the Murray-Darling Basin, changes and the changes in runoff, both in terms of percentage change, which is shown here in this middle column, and then the change in runoff in millimetres on the right. And so you can see that there's some variability from the very dry to the wettest scenario, and in fact under the wettest scenario, and these are based on an ensemble of different global climate models. Some of those models predict a slight increase in rainfall in the northern Murray-Darling Basin, whereas the majority of them are predicting an overall drying effect. And so most are predicting significant reductions in the order of 10 to 20% in runoff over the historical average. We did some work, some colleagues, and again, this is colleagues from Griffith University, but also another colleague, Annalie de Oliveira from Brazil, who spent some time at Griffith University in Australia. We did some work to try and predict what these climate change scenarios might mean in terms of fish diversity in these rivers. And Annalie's work was very alarming, in fact, in so much as it really paints a picture of major reductions, particularly in the northwestern part of the Murray-Darling Basin, major reductions in species richness over the long term as we undergo the predicted drying under a changing climate. So these plots show the number of species that are expected in different regions of the Murray-Darling Basin. And you can see that actually it's the southeast, which is currently has the highest species richness, but even in those areas, the model scenarios forecast species loss. And so I must admit, when we first looked at these predictions, I was perhaps somewhat skeptical and thinking they were a bit of an exaggeration of what my if you like, my gut feeling would tell me we might expect. But when we've seen the impacts of some of these heatwave events and how significant they are and how widespread these fish kills have been in recent years, it does actually start to make me think that these predictions are maybe not so unrealistic. So when we look at changes in rainfall, I talked at the start about the fact that water security is going to impact not just ecosystems, but also other water users. There's a suite of impacts that we foresee for the basin, and farmers and agriculture industry is already starting to adapt. So we're seeing a shift towards more drought-tolerant crop varieties. Farmers are changing already what crops are grown where. We're seeing, for example, a sudden shift in the regions where cotton is growing, which historically was grown only in the northern part of the Murray-Darling Basin. There's also potential shifts away from permanent plantings towards annual crops that allow greater flexibility in water use. But in some parts of the basin, we'll almost certainly see an overall reduction in both permanent and annual crops due to changes in water availability. And this graph here shows what we refer to as the goiter line, which is a line that was drawn a long time ago by an early horticulturalist in Australia, which identified effectively the line north of which it was considered too dry for cropping. And there's already talk of the fact that that line now has shifted somewhat southward due to changes in rainfall. I just want to highlight here an interesting paper that was published in a couple of years ago, which talked about the biological impacts of climate change as being a combined response to both press and pulse disturbance events. And so I think when we look at the fish kills that have occurred in recent years in the Murray-Darling Basin, they really demonstrate this model quite nicely, that we have this long-term variability in climate overlaid with short-term weather extremes, the heat waves that I alluded to earlier. And if we combine that with climate change, then the experienced weather is actually one of both long duration and short duration variability. But when you combine the climate change signal, what we see is greater frequency of these extreme events that, if you like, exceed the tolerance of the biota. And what we would expect is that as those events become more frequent, populations will have greater and greater difficulty in actually recovering. The resilience of populations will be diminished over time. And so there's no single threshold of conditions that will lead to population losses. It will be a combination of extreme events over time, reducing the population viability. As David mentioned earlier, in terms of water security options in coastal regions, we have opportunities to adopt technologies like desalination, where we've got plentiful supply of saline water, which can be treated nonetheless at a very high cost. And in fact, in Melbourne, in the southeast of Australia, in 2012, there was the construction of what was then the largest desalination plant in the Southern Hemisphere. And it can meet up to 2/3 of Melbourne's water needs. But in those inland regions like the Murray-Darling Basin, there are far fewer alternative water supplies available. And so we're much more having to look at novel approaches like water reuse to meet basic human water needs as well as those of the environment. So an emerging area of research for the basin is understanding the various adaptation pathways of how we can adapt both our management of ecosystems, but also our human and social systems as well, to actually survive in a drying climate where there's less water available. I'll finish up with a bit of a plug. We've just recently published a book, an edited book, which was led by an initiative led by Barry Hart, but which includes a diversity of chapters talking about both historical and future water management issues in the Murray-Darling Basin, and it goes into great detail on some of the issues that I've touched on this morning. So with that, I'd just like to thank everyone, and I'm happy to take any questions. Thank you.
Thank you so much, Dr. Bond. Your speech has shown us how careful we need to be about planning water use and also changing old bad habits to avoid natural disasters. Also believing that we could be more positive, maybe if humankind changes, but well, we have some questions here. And the first one is about the episode that happened last year, at the beginning of last year, at Murray Darling Basin. And it's actually addressing the fact that do you believe it was only due to droughts or also because of the bad habits used in agriculture due to inappropriate irrigation processes?
Yeah, it's a very good question. And I should preface this by saying that we have a very sophisticated water entitlements and allocation system in operation now within the Murray-Darling Basin. There's been a long period of water reform in Australia that largely has both been aligned with but also driven an increase in the value of water. And so the high value of water that now exists means that we put a lot of effort into tracing who's using water and ensuring that it's used appropriately and legally. Now, there have been a few instances where, for example, there has been illegal use of water and those illegal practices have been prosecuted. But broadly speaking, our assessment was that the water use practices have not contributed to the overall reduction in flows that were reaching that part of the Darling River system at Menindee. But there have been there are some licences which allow a small number of water users to access water at particular times in dry periods, which we think potentially increases the long-term risk to ecosystems and perhaps reduces the capacity of those populations of fish to recover. So, and those are specifically what are referred to in a technical sense as Class A licences, which allow access to water at particular times. And we think that by removing those Class A licences, it would perhaps increase the capacity for ecosystems within these dry river systems to actually be more resilient to drought cycles. But in terms of whether or not agriculture contributed to the lack of water in Menindee in 2018 and 19, that wasn't our overall conclusion. We think it was more to do with drought and potentially, again, an intensification of drought from climate change.
Thank you so much. I have another question. How is the engagement of the traditional communities at Murray-Darling Basin? Do you have actually an active participation of traditional communities like Aboriginals and the fishermen?
Yeah, great question. So there has been a huge shift in understanding both levels of the community as a whole, but in particular Indigenous communities, and the fact that for a long time they were excluded from debates about water use. And so for a long time, discussions about water use were dominated by, I think, the industry and agriculture. We now take a much more community-based approach to discussions about water use. So there's a lot of effort to make sure that all sectors within the community are consulted and have a say in water use discussions. It doesn't mean to say that everyone gets equal access to the water. There's still a very, it's very much within the entitlements framework, largely under the control of the irrigation sector. But yeah, there has been a strong shift to make a stronger effort towards community engagement generally, but specifically Indigenous communities, and to make sure that their views and their understanding of the river system is incorporated into how we think about and manage the water.
Very interesting. Your say was interesting because it made us reflect that some people take the value of water for granted, but once there is a dispute in water use or any kinds of conflict, we see that it's actually very valuable, and then people
That's
start
right.
taking it into
Absolutely.
consideration. There is another question here. It's a very naive question, but at the same time very important because it makes us reflect as a human being. The person is saying here, the attendee, we live here in the largest rainforest of the world. How can we collaborate to reduce the impact of global warming?
Yeah, so I mean, I think obviously at a national level, it's really important. I think, this is my personal view that each country is contributing in its own way to reduce global emissions. But we know already that even if we were to meet some of the targets that have been set, that we simply cannot prevent some level of global warming over the next 100 years or so. And so I think a major focus for the work that we do, say working within the water sector, is about understanding how we can best adapt to the changing conditions and what opportunities there might be to mitigate the impacts of the warming that we know is now inevitable. I think that's at one level a really important aspect of the work we do. It doesn't negate the need to continue to focus on that challenge of the longer term reduction in emissions.
I think maybe the first step would be to participate into the water management in a local level, so then you can start making a difference at your community, right?
Absolutely, yep. Yeah, so I think there are things that can be done at all levels, from a local level to a regional level, a state level, at a catchment and national level as well.
Thank you, Dr. Bond. There is a question here about one of your graphs. It is saying that there was a graph you showed about the rainfall anomalies between 1995 and 2016. So they're asking here if there is any kind of historic documents or, maybe the opinion coming from traditional communities saying that there were similar events like that with rainfall anomalies in the past, before this data you reported there.
Yeah, great question. Yes, there are a number of published studies, for example, that I'm aware of, where a number of techniques have been used to try and reconstruct historical drought sequences well back in time, beyond the instrumental record where we actually have rainfall data. One of the techniques that's widely used, for example, is using tree rings to actually characterise tree growth, and we know that that's affected not just by water availability. It can also be temperature, but in some areas it's seasonal lack of water availability which is the major limiting factor on tree growth. And so that's one approach that's been used, for example, to reconstruct drought anomalies and pictures of rainfall anomalies over hundreds of years. And another is in some shallow wetlands, for example, the salinity of the water is highly sensitive to rainfall and the water balance. And those changes in salinity then lead to changes in the composition of diatoms and zooplankton, with different taxa, again, having, in some cases, quite narrow salinity tolerances. And so those periods of lower rainfall, which would normally correlate with higher salinities, tend to show up in sediment cores, which can be dated to, again, align the composition of the fauna in those cores through time to cycles of wet and dry. So yeah, we know that there has been historical periods with significant rainfall anomalies, and we also know that broadly we are, the Australian continent has been going through a drying phase for a long time.
Thank you so much. Could I ask you another question?
Sure.
There is here one consideration that I could see it myself about Melbourne, that people say everybody has a tank beside their houses and they do not wash their sidewalks using the water supply system, but they do use their tanks, the ones that they built on their houses. So the question here is, when did it start? Did it start after the big crisis that you had, like, I think 20 years ago, right?
Yeah,
or
correct.
has it always been like that? So here they're asking, is there any chance that people change this bad habit in Brazil based on your experiences? This is a good question.
Yeah, it's a great question. And in fact, it was a really remarkable change in Melbourne that took place during what we refer to here as the Millennium Drought. So the Millennium Drought went from about 1997 through to 2010. And in that time, the water supplies in Melbourne started to get very low, and there was a lot of concern about that in terms of the potential longer-term risk that the city could potentially run out of water, which is why that desalination plant was constructed. But as you can imagine, constructing something of that scale, there's a long lead time, and so as well as those sort of policy responses, the government also imposed quite significant restrictions on water use, domestic water use. So as you say, people it was actually illegal to use the hose to, in some cases, water lawns even in people's gardens. So there was major restrictions put on domestic water use. But one strategy that people then adopted to increase the capacity to water their garden and so on, as you say, was to build or to put in place domestic rainwater tanks alongside their houses. And the effectiveness of those rainwater tanks is highly dependent on the rainfall patterns of the region. So because our rainfall is quite variable in Southeastern Australia, you actually need a very large tank to ensure a reasonable level of security of water from your tank. Even it's a very similar problem to the one that is faced from a central supply system as well. But it's the daily water use in Melbourne went from somewhere around 240 down to 155 litres a day. So there was a really big reduction in average water use. It has gone up again since then with the relaxation of restrictions. But certainly it was a period which really heightened people's awareness of the problem.
Mm-hmm. At least people could get adapted to the new rules based on their new scenario. That's good. Yeah. Thank you so much, Dr. Nick.
Thank you.
Lovely to have you here tonight. Thank you for sharing all your experiences with us.
No problem at all. And thanks to everyone who's been able to attend.
Thank you. We hope to see the three of you again soon in a future event. Well, now I would like to start the end of our event, presenting the last considerations. Well, first, I would, of course, like to thank all the speakers, because I know how busy you are, and I know it's not easy to find a spot on your agenda to have the three of you coming here and joining us tonight. So really, we really appreciate it. Thank you so much for being here with us. We would also like to thank all the attendees, because you know that everybody has been so busy with this virtual life, the normal reality of everyone. So it's very nice to have this large audience that we had tonight, to welcome our international speakers to our local event. We hope that the actions, that the strategies that we learned today with these speakers can eventually take place here in our home country. And we also would really appreciate if we could have actions like the ones of these webinars could continue happening to improve the community participation in watershed management worldwide, not only here, but also in Australia and every country in the world, because water, as we know, is a very essential resource. We cannot live without it. So let's start having structural programs to promote education towards the water use. I would also like to acknowledge the support we have been having from the Tropical Water Research Alliance and also the IFSP teams, including professors, students, and all the voluntary collaborations. Have a great evening, everybody. We hope to see you next week on our next webinar that will be about the technologies and methodologies used for the integrated management water resources. So see you next Thursday at 6:30 p.m. Have a nice rest, everyone.